elections on the horizon. 4 weeks left. Yeah. Less than that, 3.5 after today, I think. So yeah, I feel the same way. Let's see. Yeah, there's a last test. What did you think we were going to do for the rest of the semester? There's no final, but there's a test on the last day of class. So otherwise, I don't think I could get you guys to show up. So yeah, you'd be surprised. Okay, so should we just go over the practice exam? Okay, so so the first couple of problems are really, well, first one's dealing with just the fundamentals of FM and FM signal. The second one is dealing with a frequency multiplier. And the third one's a super heterodyne receiver for FM. And then the fourth one is this commutator or telemetry problem. So give you the formulas there at the bottom of the page. So this says this is an FM signal. What's the carrier frequency? Well, that's this frequency. So it's made it easy for you. It says 2 pi times 94 times 10 to the 6 times t. So the carrier frequency in hertz would just be the 94 megahertz. Okay. So I was giving you 3 points right there. Just copy that number down. Okay. The frequency deviation, that gets a little tougher. Probably the easiest way to get that, although you could compare, I think, possibly to some formulas in the book, is if we say that the instantaneous phase is 2 pi 94 times 10 to the 6 t plus 2 sine of 2 pi 30 times 10 to the 3rd t, then the instantaneous frequency, which is what FM is based on, it's the derivative of the phase angle divided by 2 pi. Okay. So take the derivative of this part, divide by 2 pi, you're going to have 94 times 10 to the 6, okay, which is the carrier frequency. Okay. The instantaneous frequency is the carrier plus the frequency deviation. If we take the derivative of this next part, the derivative of sine is cosine, but I'll pull out this 2 pi 30, but again, I'm dividing by 2 pi. So this would be 60 times 10 to the 3rd cosine of 2 pi 30 times 10 to the 3rd t for the instantaneous frequency. So what this means, because cosine goes between plus or minus 1, okay, when cosine is 1, this would be 94 meg plus 60 kilohertz. When cosine is minus 1, the minimum would be 94 meg minus 60 kilohertz. So the instantaneous frequency is really the carrier plus or minus delta F. So delta F, and I think that formula is probably, or something like it is in the bottom of the page here. Here it's written as KF times MT. Okay. But it also says that the minimum and maximum frequency here. Okay. So all of this, I guess, just to say, the delta F here is 60 kilohertz. Okay. Because it can go 60 kilohertz above and 60 kilohertz below the carrier. But the delta F is just the deviation from the carrier. It's not two delta, it's not the total deviation. Okay. So is that okay? Okay. What's the maximum frequency in the message? Okay. So this is the message now, because instantaneous is the carrier plus KFMT, where this is KF. But the message, looking at this, the maximum, there's only one frequency in this, so it's also the minimum frequency, but it's 30 kilohertz. This is the 30 kilohertz tone. Okay. So what's the difference between the maximum and minimum instantaneous frequencies? Again, that's actually 2 delta F or 120 kilohertz. And because the instantaneous frequency is varying around the 94 megahertz, sinusoidally, but it's going, as this thing goes from, 1, you'd have 94 plus 60K down to -1, where it's 94 minus 60K, but the total variation there is 120K. Okay. Now, what's the difference between the maximum and minimum frequencies in the spectrum? Okay. It's really asking for, if you take the Fourier transform and, you drew this, what's the difference between the largest frequency in the spectrum and the minimum frequency? That's the bandwidth of the signal. Okay. And it says right there, the bandwidth of the signal. So how do we get the bandwidth for FM signals? Does any of the formulas at the bottom of the page look promising? Carson's rule, right? So that's how you get so what is this? This is E. So bandwidth is 2 delta F plus FM. Okay, so it's 2 times the frequency deviation plus the maximum frequency in the message. So in this case, it's 2 times 60K and then plus 30K. So that would be 90K, and 2 times that would be 180 kilohertz for the bandwidth of the FM signal. Okay. Questions? Okay, the power of the formula there again is in the box, but FM has a constant amplitude. So unlike amplitude modulation, where the power actually depends on the modulation index, it doesn't here. It's just a squared over 2. Okay. And I mean, that's the same as the power of any sinusoidal signal. It's the RMS voltage squared, the amplitude divided by square root of 2 squared, or the amplitude squared over 2. So it'd be 100, it would be 10 squared over 2, or 50 watts for that one. Okay. Okay. Any questions on 1? Okay. So 2, an FM transmitter transmits a carrier. So I usually mark up the diagram at this point. Transmits a carrier at 100 meg. So this is coming out of, actually, so we've got a narrowband FM, our message coming in, a local oscillator, and then we've got our transmitted signal. Oh, I'm sorry. Frequency multiplier, then the mixer. And then our antenna, okay, or a power amplifier in the antenna. But FM transmission system has a carrier frequency of 100 meg, so that's the radio station we're tuning to. The modulating signal has this, so this is the message, has a maximum frequency of 20 kilohertz. So FM is 20 kilohertz, okay. Or that's sometimes written as W, the maximum frequency in the baseband signal. The frequency deviation of the transmitted signals required to be 80 kilohertz. Okay. The indirect FM system is used to generate the narrowband FM uses a carrier of 400 kilohertz. So that's here, 400 kilohertz. And then a corresponding frequency deviation. And it's less than, does it say 400 hertz? Less than 400 hertz. Okay. So at least that helps me when I mark everything directly in the diagram. That helps me remember, you know, what I've got to get to. Okay. The first question is, well, what's the bandwidth of the and this is Carson's rule. It's of the transmitted signal. So here it's 80 kilohertz is the deviation. And FM isn't changed through the FM system. Okay, so the maximum frequency in my message is 20 kilohertz throughout here. So that would be 200 kilohertz, which is the same actually as for FM radio. How many frequency doublers are needed in the multiplier stage? Okay, so the multipliers actually change my delta F. They also change the carrier frequency. But the mixer, this thing, does not change delta F. Okay, so I pick the number of multipliers to get the delta F I need. Okay, so I need to find N such that 2N is 80K over 400. That's 800 over 4, or 200. I mean, you could solve for N using logarithms, but you don't really need to do that if you remember your binary. I need 8 bits. 8 bits I can represent 256 different things. 7 bits is 128. So I know it's between 7 and 8, right? But I've got to round up. Okay. So n is equal to 8, okay, which means I'm actually going to get a multiplication of 2 to the n, or 256. I have to have an integer number of these doublers present. Okay. So this is the answer to B. How many frequency doublers? It's 8 doublers, but then they increase, the multiplication is by 256. To what should the frequency deviation of the narrowband FM component be adjusted? That's actually the, let me call this delta F1 and delta F2. That's actually delta F2, but it's not the number of doublers, but actually the multiplication factor. And by rounding up here, this should be less than 400, which is the maximum value to which I can adjust this. Okay, so that's why we round up instead of rounding down. Okay, if I round down, that would require a delta F greater than the 400 I can get. So I don't know what that is. So if you have a calculator, 312. Okay, which is less than the 400. Okay. Okay, so now we're back here. So this is doing 256. So at this point, this delta F will be 80K. We've got the delta F, and that won't be changed by this. But the other part I need is, I really should have called these 1, 2, and 3, I guess. But I need the carrier frequency here, which is 256 times 400. So 1024, 102.4 megahertz. Right? I think 256 times 400K, 102.4 megahertz. Okay. And then, so I've got 102.4 megahertz coming into my mixer. I want 100 megahertz out. So what's the required local oscillator frequency? 2.4, okay. And there are always two answers to these. What would be the other one? Yeah, 202.4, right? Or 202.4 megahertz. Because you always get the sum and difference frequencies out. So again, there's always two choices for any of these, two choices for the local oscillator, two choices for the possible output frequency, two choices for the input frequency, to, the one we call the image. Okay. Any questions there? Okay. Again, I want to, can I get it all on there? Yeah, just about. So super heterodyne. Receiver is tuned to receive an FM radio signal. So that this is coming in. So audio, IF, This is my RF amplifier. And let's see, the carrier frequency coming in is 91.5. And I'm also given that the maximum frequency in the message is 15K and delta F is 75K. The receiver uses an intermediate frequency of 10.7 megahertz. Okay. So I think that's all the information that I'm given. So the RF amplifier just amplifies the signal. It doesn't change the carrier frequency, but that's what this mixer does. So 91.5 coming in, I need 10.7 out. And there are two choices. It'd be 91.5 minus 10.7 and 91.5 plus 10.7. But you're told high side conversion, so that means you want to choose the local oscillator frequency that's above the incoming. Okay. So F low is 91.5 plus 10.7, or what is that, 102.2 megahertz. Okay. So the difference with the 91.5 would be the 10.7. I would also get, 102.2 mixed with 91.5, I get the 10.7. I'd also get the sum frequency out of here. But the intermediate frequency amplifier filter is only going to pass through the 10.7. And then it also would filter out adjacent channels. Okay. Now B is, what's the image frequency to this? So that's asking what other frequency here, other than the 91.5, when mixed with 102 would give me 10.7 at the output. Okay. Well, the 91.5 is the difference between these two. So the other frequency, the image frequency, would be the sum of those two. So that would be what, 112.9? Okay. That would be the other frequency here when mixed, when mixed with 102.2 megahertz would give me the 10.7. Okay. Now, again, that the RF amplifier would be responsible for filtering that guy out. It would just pass through the FM band and then filter out anything else. Because if it actually came through, if there were an FM station operating at this frequency, it would actually be leaked through. I'd hear both stations. Okay. And then the bandwidth of the IF amplifier, so this would have to be the center frequency, because this is the carrier. The bandwidth would be 2 delta F plus FM. Okay. That's the same delta F and FM as the incoming. Okay. The mixer changes the carrier. It doesn't change either delta F or FM. Okay. A frequency multiplier would change delta F, but a mixer doesn't change delta F or FM. So it's 275K plus 15K. So that's 80, 90, 180 kilohertz for the bandwidth. Now, what's the bandwidth of the audio amplifier? we just count the positive frequencies. If you're trying to count both positive and negative, it would just be the detector recovers my original baseband signal. Okay, so my detector, so that the carrier frequency would now be 0, and then the maximum frequency would be 15K FM. Okay. So when you modulate this up, then it has a 30K bandwidth. But as a baseband signal, we call the bandwidth of this just 15K, the range of positive frequency. So it's not the entire width. It's just the positive frequencies that are in the signal, which is consistent with, when we modulate it up, it's the range of positive frequencies then is 30K, but the bandwidth of the audio amplifier is just 15 kilohertz. And I gave you a couple homework problems with these, so make sure you've looked over these commutators, subcommutators. Okay. Because there will be a related problem. Okay. So again, we've got a 6-channel multiplexer, and then 6 signals we want to transmit. But we also have to transmit a marker. 1, 1, 0.5, 0.5. So the required sampling frequency but we're using a multiplexer that has 6 channels and is sampling at 12 kilohertz. Okay. Which means this signal is actually going to take up 2 channels. Okay. Okay. As will this one. Okay. So at this point, we've got 5 channels already taken up out of our 6-channel multiplexer, right? 1 for the marker, and then each of these signals are using 2. So we can only cross our fingers and hope that these other 4 will fit into that 1 channel. So this is 2K. So what if I get, what's 1/4 would be 3K. This is probably the easiest way to do it, right? That sums up to 5. The actual sampling frequency would be 24, which is fine. This is 24, it's greater than the 20. 1/4 of 12 is 3K, 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 3K. As long as I exceed the required Nyquist rate, I'm great. Okay. So, looks like that all fits. So we have a main commutator, Fs equal 12 kilohertz. So this would be 72 kilohertz. I'll put the marker here. Okay. And then signal 1, and we need to make sure that they're equally spaced within consecutive frames. So I'm going to this sample, skip to this sample, skip to this sample, skip to so on and so forth. Okay. Now I want to do the same for S2. sample, skip 2, sample, skip 2, sample, skip 2, so that they're equally spaced within the frame. And so, my frame would be a marker, S1, S2, and then I'm going to get this other pulse here, which has, actually it's going to alternate S3, S4, S5, S6 in consecutive frames, but then I get S1 again, and then S2, is that my 6, and then the marker repeats. Okay, and then I'm back to S1, and then S2. So the first time through, this is going to be S3, but in the next frame, it would actually be, S4. And then I'd have S1, S2, and then the next frame would be S5. So I'm getting greater than 12 kilohertz sampling of S1 and S2, but then less than 12 kilohertz, 3 kilohertz sampling of S3, S4, S5, and S6. So for this remaining channel, I really just need a 4-channel multiplexer sampling at a 3K rate. 1, 2, 3, 4. S3, S4, S5, S6. Okay, and then that would be here. This has to be 12K. So I can get its clock from my 72 kilohertz clock. Okay. There were 2 more problems like that assigned in the homework last time, and then I posted the solutions to them. So make sure that you review those. Are there any questions on this? Here it's just divide by 6 to go from the 72 to the 12. So let's see, I didn't read the whole thing. It says other 2 and 4 channel multiplexers are available, so we're good. So I used a 4-channel multiplexer. And then note here, the effective required sampling rate coming out of this is actually 12 kilohertz, right? The 4 samples times the 3K. So that's actually generating a signal that we would need to sample at 12 kilohertz. Well, that's exactly what 1 channel of this is doing. Okay. But S1, we're actually effectively sampling at 24 kilohertz, and the same as S2. The other 4 signals we're sampling at 3K, which is above the required sampling rate. So all of these fit into then just 1 signal, 1 wire that we could run instead of having to run 6 different wires. So that's the purpose of this, is to actually save copper, be able to, it's time division multiplexing here with these different signals have different sampling rates. If they're all at the same sampling rate, then it's a lot easier. Then it's like the telephone system we talked about last time, the T1 line. Questions about this or other questions? Should we just all stand here for a while or sit here, or would you like to just leave early? Mark's ruining it, so he's going to ask a question. Okay. This it's just dividing by 6. So 72 kilohertz clock coming in, just dividing it by 6 to get the 12 kilohertz clock I need for that one, just to showing that the clocks are synchronized. So I don't know if you talked in the, remember in your digital logic, you probably talked about using a counter as a clock divider. Maybe not. Okay. But you need a counter here that essentially divides the incoming clock by 6. So if this thing is so if this is the clock coming in, it's really pulling out every 6 pulse. So it's generating a related clock that is at 1/6 the frequency is all it's doing. And you can do that with a binary counter that counts up to 6 and resets is typically how it's done. S1, S2, S3, marker, yes. Because we're going through these so in the next frame, it would be S5. Then the next frame, it would be S6. Then the frame after that, it would be S3 again. Okay. So we're actually getting one S3 sample every 4 frames. Since the frame rate is 12 kilohertz, that means we'd be getting an S3 sample every 3 kilohertz, 1/4 of the frame rate. And then similarly for S4 and S5 and S6, they're effectively sampled at 3 kilohertz. Now at the receiver, I've got to pull all this stuff out and route them to, it's 6 different signals here that I have to, pull apart and interpret, they're from 6 different sensors. But instead of having to run 6 different wires to this remote location, I only have to do one, or, I could modulate all of this and transmit it wirelessly as one signal now too. All right, any other questions? All right, that's it. So have a good weekend.